Today we're going to talk about solving general 2x2 matrix games. We've just started analyzing uh, matrix matrix games representing two-player zero-sum games, where the payout function is given in the form of a matrix. We've just started talking about these, but already we should see that 2x2 games are easy to solve. Why? For any 2x2 game, we really have only two things to look at. First, we can check to see if there's a saddle point. If there's a saddle point, we already know that the value at the entry at that saddle point is the value of the game, and both players can achieve that value by playing pure strategies to arrive at that saddle point. What's a saddle point? Well, remember, saddle point is an entry in the matrix, which is the smallest entry in its row, and at the same time the largest entry in its column. If there's no saddle point, just do what we've done before and find the equalizing strategies for both players. The expected return with these strategies will be the same for both players, and it will then thus be the value for the game, because each player can assure that he or she does no worse than that number, that value, which the player gets by using the equalizing strategy. Let's see some examples. Let's say we have the matrix game with payoff matrix 2, 1, 3, 4. Remember, player 1 picks a row, player 2 picks a column, and all of these payouts represent payouts from player 2 to player 1. So this game clearly is one where player 1 is going to win something. The question is, what is the value of the game? Well, it's pretty easy just to look at this and see that this number 3 here is the smallest entry in row 2. It's also the largest entry in column 1. What does that mean? That means if player 1 plays a pure strategy, always play row 2, and player 2 plays a pure strategy, always play column 1, they'll arrive at this payout 3. Player 2 pays $3 to player 1. Now, if player 1 pays this pure strategy, player 2 can't do any better than that. It's only worse if player 2 does column 2. If player 2 plays the strategy of always playing column 1, player 1 can't do any better than just playing row 2. So both players cannot guarantee any better outcome than a payout of $3 to player 1. Thus, the value of the game is 3. But now let's look at this second matrix game. We have the same numbers, 1, 2, 3, and 4, but in a different order here. And you'll see that there's no saddle point. If you look at the row minima, what do we get? We get a 2 here, and we get a 1 here. If we look at the column maxima, we get a 3 here, and we get a 4 here. There's no common number among these, so there's no point which is at the same time a row minimum and a column maximum. In other words, there's no saddle point. Now, you might ask, is it easy to tell, looking at a game, when there'll be no saddle point, other than just check each of these numbers or do the computation that I just showed you before? Well, with a 2x2 game, there are several different ways we can look at this. Notice here that the entries going clockwise, starting at 3, they get smaller, bigger, smaller, bigger. Whenever you see that pattern, you can check this very easily, and I want you to explore this. Whenever you see that pattern, smaller, bigger, going around clockwise or counterclockwise, you'll see that there can't be a saddle point. What happens when there's a saddle point? Here you see that going clockwise, say starting at the 4, you get smaller and smaller. Anytime you have, when you're moving around in a clockwise or counterclockwise direction, entries that go smaller, smaller, or bigger, bigger, you're going to have a saddle point. So try to play with that. Try to convince yourself that this is the case. Now, what do we do here when there's no saddle point? Well, we play the equalizing strategy. How do we find the equalizing strategy? Well, we'll see that in just a minute, so we'll compute it then, and we'll come back here. Here's the general case, just general numbers A, B, C, and D. I've written them clockwise, A, B, C, and D, like this. And if there's no saddle point, as I already said, we have a couple possibilities. Either starting from A and going clockwise, we get smaller to B, then we go bigger to C, then smaller to D, and then bigger back to A, or kind of the other way around. From A, we might get bigger to B, smaller, bigger, and smaller. One of those two situations has to happen if there's no saddle point, because in the other case, when you have 3 in a row going around clockwise, where they get bigger and bigger or smaller and smaller, then we're guaranteed to have a saddle point. Now, how can we compute the equalizing strategies? Well, we assume player 1 chooses a strategy of probability row 1 with probability P and row 2 with probability 1 minus P. Then we compute the expected returns if player 2 chooses column 1 or column 2. Well, if player 2 chooses column 1, the expected return is this, AP plus D times 1 minus P. You take A, that outcome, times its probability, plus D, that payout, times its probability. If player 2 chooses column 2, you get an expected return of B times P plus C times the 1 minus P. And when we equate these, that's what we mean by an equalizing strategy for player 1. We choose the probability P that gives us an equal expected return regardless of what player 2 does. We can solve this equation for P very easily. You can see the algebra here. The result is that the probability P is just given by C minus D over A minus B plus C minus D. It's easy to see then that 1 minus P is just A minus B plus C minus D over itself minus this, which just gives you A minus B over A minus B plus C minus D. So player 1's equalizing strategy is this, and the expected return then is just what you get when you plug in P here, or the same, that should, of course, by what we just computed, be the same as what you get when you plug in P here, and that return will be AP plus D times 1 minus P. That's this one. And you plug in what P is and what 1 minus P is, and you get the expected return as AC minus BD over A minus B plus C minus D. It's easy to look at this matrix and kind of remember that. What is AC minus BD? Well, that's just the determinant of this matrix. And what is the denominator? A minus B plus C minus D. It's just going clockwise here. The first one minus the second, plus the third minus the fourth. So you take the alternating sum going clockwise, and you divide the determinant by that number. Now, this is the equalizing strategy for player 1. Player 1 can guarantee an expected return of this amount by playing the equalizing strategy. Whatever player 2 does, it doesn't matter. This is the expected return that player 1 can get. If we do a similar computation for player 2's equalizing strategy, and you see here the computation is similar, we are going to assume player 2 plays column 1 with probability Q for column 1, and 1 minus Q for column 2. Then we ask what is the expected return if player 1 plays row 1. We would get just A times Q plus B times 1 minus Q, that's this. And if player 1 plays row 2, that the expected return would be DQ plus that should be C times 1 minus Q. This should be a C here. And when you solve this equation for Q, we do that just like we did before. I didn't show all the algebra here, but it's very easy to compute that Q will be C minus B over A minus B plus C minus D. Then, of course, 1 minus Q will be A minus D over A minus B plus C minus D. And then that return that player 2 will expect will just be the value we get when we plug in Q to in this formula, or the same thing if we plug in Q here, since of course those have been equalized now. And that will be AC minus BD over A minus B plus C minus D. Notice that this is exactly the same formula we got before. And what does it mean that these are the same? It means that player 1, using player 1's equalizing strategy, can guarantee this expected return. Player 2, using player 2's equalizing strategy, can guarantee this return. In other words, each player can certainly guarantee that he or she does no worse than this amount. And there's no way either player can do better if the opposing player is using his or her equalizing strategy. So what do we call this? We call this the value of the game. So that value of the game is given by AC minus BD, that's the determinant of the matrix, over A minus B plus C minus D, that's that alternating sum, starting in the upper left and going around clockwise. And the way each player can achieve the value of the game is to use the equalizing strategy. Here's the equalizing strategy for player 2, C minus B over that denominator and A minus D over that denominator. And for player 1, the equalizing strategy would be to choose P equals C minus D over the denominator, and 1 minus P is A minus B over that denominator. So they both have the same equalizing strategies there. I'm sorry, not the same. They both have similar equalizing strategies. These numbers are a little bit different for the two, but they have the same value, the same expected return, which is what we call the value. How does that play out here? Well, what is the value of this game with 3, 1, 2, 4 in the matrix? Well, the value will be the determinant, which is 12 minus 2 is 10, over the alternating sum, 3 minus 1 plus 4 minus 2, which is 4. And of course, that's the same as 5 halves, or 2.5. What will player 1's equalizing strategy be? Well, player 1 uses, again, this formula. P is C minus D over the alternating sum, and 1 minus P will be A minus D over that same alternating sum. So that alternating sum is 4, so we're going to use P equals C minus D, which is 2. So P should be 1/2. Of course, 1 minus P will equal 1/2. And you can see that that will work. If player 1 plays row 1 half the time and row 2 half the time, player 1 will get exactly a return of 5 halves on average, regardless of what player 2 does. What is player 2's equalizing strategy? Well, we had that here. Player 2 picks Q as C minus B over A minus B plus C minus D, which means Q will be something over 4. The C minus B will be 3. And of course, then 1 minus Q will be 1/4. So player 2's equalizing strategy here is different. Player 2 will want to play this first column 3/4 of the time, and the second column 1/4 of the time. And you can compute very quickly that with that strategy, the expected return again will be 5 halves, or 2.5. And remember, that's a payout from player 2 to player 1. Player 2 wants to get the smallest possible number here. And using the equalizing strategy, player 2 knows that the expected return will certainly be no bigger than this. In fact, it will be exactly this, regardless of what player 1 does.